Welcome back to the second part of building a simple neural network image classifier with Keras. In the second part of this workshop, we're going to be testing with our own data. Our goal for this part of the workshop is to use our previously trained model and predict the label of images outside the MNIST set. We're going to be using actual hand-drawn images in this case. All previous libraries from the last part of the workshop are going to be used, but we're also going to be introducing two new libraries. The first one is OpenCV Python, which is a computer vision library for image processing. The second is Matplotlib, which just helps us visualize our images. Here's a workflow for our project. We're going to load in our model that we've saved from our previous training session. We're going to load in an image. We're going to process that image to be able to be fit into our model input. We're going to make a prediction on it, compare that with the actual value, and then repeat this process for all image in the test set. After that, we're going to calculate the accuracy of the predicted images. So without further ado, let's get to coding. So before we get started on any coding, here is the test set we're going to be using. So as you can see, it's just a directory of PNG files, and they're sorted in order by the name. So each image is actually just a hand-drawn drawing of a digit, and you can do this simply with like any paint editor or like a drawing app online. And along with that, I have a CSV file of the labels corresponding to each image, and they're corresponding to the order of which the directory was sorted in. All right, and so next, just navigate to your working directory, and like I said, we're going to have to install the packages that I've mentioned previously. So if you haven't installed the packages from the last part of the workshop, check that out and go do that. Otherwise, the new packages we're going to install are called Matplotlib, as well as OpenCV Python. So just run the pip install command. I already have these installed, so I'm actually not going to run these or run this command. So next, once you've done that, just open your text editor or your IDE that you're going to be using, and just open your project. Okay, so within our project, let's actually go ahead and create a new Python file. Let's call this test set classify. Okay, now like before, let's go ahead and start with some import statements. So first, we're going to be using our OpenCV method, or our OpenCV package, and this is actually called CV2 in this case. So let's import CV2, and we're going to import NumPy as MP. We're going to import OS. We're going to import TensorFlow as TF, and we're going to import matplotlib.pyplot as PLT. All right, now let's get started by creating some variables to represent our paths. So the path to the folder containing our test set is within the directory of our project, and it's just going to be in a subfolder. So let's call path, or actually let's call folder path equals, and let's make this a string, and it's going to be test set, and specify that as a folder. And we also need the path to our label CSV file. So that's also within the project directory. So we can just make a new variable called label path and set that equal to just labels.csv because it's actually just within that project directory. So we don't need to access it through a file or a folder. And these are our paths. So next, we're going to take our CSV file, and we want that to be read into an array. So we can do that with the built-in method from NumPy called gen_from_text. So let's create a variable called labels, and this is going to be a NumPy array. And we're going to make this by using the numpy function called np.gen from text. And this takes in your path to the CSV file. So label.path or label_path, and our delimiter, which is going to be a comma. As you can see within our CSV file, we use commas to separate the specific labels. And here are just a few variables we're going to be using through our methods. And the first one is going to be a simple counter, which is going to keep track of the total number of images, as well as keep track of through each image which label the image is actually being considered. And we're also going to create a numCorrect variable. This is just going to help us calculate the accuracy at the end. And then next, we're going to have to load the model. So we can actually do this with a simple command that TensorFlow has, and we're going to make a new variable called model, and I'm going to set that equal to tf, our TensorFlow library, .keras, .models, and we're going to call this load model function. And we're going to take in a path to the model. But so before we do anything with this, we also need to specify one thing or make one change to the previous image classifier that we did in the previous part of this workshop. So we also, at the end of this file, we need to add this little command here. This is going to save the model to the disk to be read in through this file here that we're going to be using. And as you can see, our path name is classifier model.h5. So let's actually just copy this and then use this and load this in later. And let me just add this equal sign right here. All right, my apologies for the loud computer fan, but now let's get started on actually loading in each image to be processed and then predicted. So right now we have a directory full of our images. We want to be able to get each image from that directory. So we can just do for file name in os.list directory, and we're going to pass in the path to our folder, which is folder path. And just to make sure our directory is sorted in the way we want them to, we can call the sorted on this list to make sure that it's sorted by the file names. All right, so now we can just start by creating an image variable called img, and we're going to use the OpenCV Python library to load in our image. So we can do cv2 and .imread, which is going to be the function that loads in our image, and we're going to have to specify a relative path to this image. So right now, if we just pass the file name, it's going to pass in the file name relative to this directory. So we actually are going to use os.path.join, and we're going to join the folder path with the file name. This way we have a relative path to the image from our working directory. All right, next we need to resize our image. Like I said before, MNIST takes in a 28 by 28 image. Right now, our images are not 28 by 28. So we can use another cv2 function, img equals, and we're going to use cv2.resize. And this is going to take in our image that we're resizing, as well as our dimensions. And in this case, it's 28 by 28. All right, let's just add in some comments real quick. So this is going to be read in image, and this is going to be resize image to 28 by 28. And here we're going to get each file name in sorted directory. All right, so next we're going to have to change our image to grayscale. So like I said before in the previous workshop, the MNIST dataset has not 3 not 3 RGB values for each pixel. Instead, it has one singular color value, which is instead how black or how white it is. So to do this, we thankfully have another function from CV2 called CVT color. And this is going to take in first our image we're going to be changing the color to, and next the color swap palette. So it's going to be CV2, and we're going to be using color underscore RGB to gray, which is going to change RGB to grayscale. And again, this is going to be changed to grayscale. All right, next, we're going to have to invert the image. So right now, the MNIST dataset encodes their image with white with 255, or with white as 0 actually, and with black as 255 as color values. While normally, and with our image, it's the opposite, with white being 255 and black being 0. So we need to invert this to stay on the same page to make sure our machine learning algorithm can actually understand the image. So we're going to invert image, and NIST encodes white with 0 and black with 255. And while normally it's opposite. Okay, so with this, we can do another CV2 function, and this one is actually going to be bitwise not, which is just going to take every value and just invert it. So let's call this on our image. All right, great. Now we need to then shape our matrices for our image into the same dimensions as we had in our image classifier. So first, we can actually do mean normalization like we did before. And we're just going to do the same thing from the previous workshop, where we subtracted its range and then divide by its range actually, and then subtracted by the mean, which is 0.5. And then now we can actually get to resizing or not resizing, but changing the dimensions of the image matrix to be ordered to fit into the model. So this process from before is called flattening. So we're going to flatten the image, and from before, remember that we reshaped our image matrix into a 784 dimensional vector because it's 28 by 28, and instead of having a square matrix, we're just going to have a long vector. So we can do the exact same thing. We're going to do this thing real quick with image equals image dot reshape. This is the exact same way we did before with -1, telling NumPy to basically find the dimension for us for that first dimension, and 784. All right. Now, before we reshape our image, we can actually use matplotlib to show us our image before we actually go and go and send it into our model. So with that, right before flattening, we can actually go ahead and use PLT, which is our matplotlib library, and .im show, which is going to show our image. It's going to take in our image, and it's also going to take in a color mapping, and in this case we're using grayscale, right? So we're going to just pass in a string grays, which is going to tell matplotlib to display the image in grayscale, and then we're going to show the image, plt.show, and this is just display image. All right, so now we can actually get to predicting with our image. So first, just for display's sake, we can just print out the file name so we know which image we're working with. And next, we're going to have to get the correct label. So remember, we have an array before labels that has an array with each of the correct label. And we also have a count variable that is counting up or it will count up for each image that we have in our directory. So we can get our correct label by just calling the array index of count. So we call labels and we call it on the count index. And because it's a CSV file, all the inputs are read as a string. So we need to cast this to an integer. All right, so this is going to be our correct label. And let's actually go ahead and now create a prediction variable that's going to be the correct prediction for our, or just a prediction that our model makes on this image. So we can use model.predict and pass in our image. So right now our prediction variable is going to be, remember, a 10-dimensional vector with each index being a probability of whether or not that index is the correct prediction. So for example, if the index 0 is 0.9, then we have a 0.9 probability that that 0 is the correct image. So because of that, we want to get the index of the highest probability. And to do that, we can use the argmax function that NumPy has. So let's create a variable called output, and this is going to be the integer value of the correct or the highest likely prediction that our model makes. So we're going to call numpy.argmax, and we're going to call prediction. And because there's only one element in this array, we just call it on 0, but this really doesn't change anything. It's just getting the only element in the prediction array. And with that, we have the predicted label. And so from here, we can do a couple of print statements to tell us what actually is being outputted. So let's say actual value of image, and we're going to call string of to cast the integer value to a string, and we're going to call this on the correct value because it's the actual value of the image, and we're going to print the predicted value of the image, and this is going to be again string cast of our output, which is going to be the predicted value. And from here we can do some calculations to help get the accuracy. So first, if correct equals output, which means that our output predicted is the same as the actual value, we can do numCorrect plus equals 1. And remember, numCorrect is our counter before that's counting the correctly classified images. And we can also, before this, actually do a print statement that says, let's say, model predicted correctly. And otherwise, we know that the model predicted the image incorrectly. So we can print, let's say, model predicted incorrectly. And we're not going to increment anything here. All right, so then we can do another print statement just to print out a blank line to make things look a little bit better. And after all that, we need to increment our counter. Okay, and so that's going to be the for loop of all the images. Next, we're going to, or once that's done, we can actually find the accuracy. So let's make a new variable called accuracy, and then we're going to divide the number of correct images classified over the total images. So we can do float of numCorrect to make sure we're using floating point division here, and divide this by count. And this is going to be the accuracy. And then at the end, we can just do a simple print statement, accuracy of model on hand drawn set, and then like before, string of accuracy. All right, let's add a few comments here. And I think we're ready to test. So one thing before we actually get to running our file, you might encounter an error that says the size is empty for this image when you call the cv.resize function. And this is because if you're using OS X like me, sometimes Mac will actually create a hidden file called like .dsstore or something, and that's going to be counted in your directory when you're actually going through each image. So if you go to your test sets directory here, if you ls, you see our images here, but right now we can't actually see the dsstore file. So if we ls with the tag a for all, we can actually see that there's a dsstore metadata file here. And what we can do is we can simply just remove with the rm command .dsstore, and this will remove that file for us. And as you can see, it's not here anymore. And now actually we can go run our file. So let's go ahead and hit run and just give it a second to load. And this is going to be our output. So let's see. And so for the first image, 0, we classified it correctly. Second one, which is 1, correct. 2, correct. 3, correct. And I think all of them are correct except for one of them, which is 7. And it predicted as 2. So maybe it saw maybe a similar, I guess, pattern that 2 has. Maybe this extra line here could make it similar to 2. But overall, those are pretty similar digits, so that's not too bad. And you can see our accuracy is 90%. And here are all the image displays for us using Matplotlib. And yeah, so this is our classifier on images that we create on our own. Alright, so hopefully that was able to give you a good sense of how to create your own test set and images to be able to pass into your model after pre-processing it and predicting the label. So from here, you can implement a way to gather images and gather images to predict autonomously. There may be like a web app or something, and connecting that to maybe like a TensorFlow.js or Flask backend with your model. Also, the convolutional neural network is a different type of neural network that actually is much more efficient for image classification. So because images, unless your image is random noise, obviously, are actually going to have much of the similar pixel values within the same cluster. For example, looking at this slide, you can tell that most of the background is just one color. And this holds true for a lot of images actually. You're not actually needing all the data. So convolutional neural networks are actually more efficient in that regard. But obviously that's for a later workshop. But yeah, so all the code for this workshop, as well as the previous part of this workshop, will be posted on GitHub. So check it out if you want to. And as always, thank you so much for watching, and I really hope you enjoyed this 2-part workshop on creating an image classifier with Keras. Thank you so much.